For 6 decades, the contract between humans and computers has relied on direct manipulation. You click a folder, the machine opens it. You navigate a menu, the software responds. That graphical user interface was architected for a local environment, housing 3 programs and a filing cabinet. It scales poorly to distributed cloud ecosystems. Today, the average enterprise employee actively uses 9.4 different applications and toggles between them roughly 1,200 times per day. The complexity of the digital workspace has eclipsed human cognitive bandwidth. When early large language models arrived, they lacked persistent memory and agency. Prompt engineering became the required method to compensate, forcing users to manually dictate roles, specify constraints, and format outputs step by step. In production environments, prompt chains break down. Human input carries inherent variance, and minor adjustments in phrasing cascade into entirely different operational decisions. Enterprise architecture demands predictable, auditable governance. A system cannot rely on how a user phrases a request at 9 p.m. on a Tuesday. When the number of digital tools outpaces our ability to navigate them, the interface itself becomes the constraint. To move faster, we have to offload the manual execution of those 1,200 daily toggles to the machine. We are shifting to intent-based execution. Users state a desired outcome, like identify and fix SEO visibility losses across priority pages, and the system handles the procedural steps. This requires large action models, or LAMs. Systems like Manus operate as general-purpose digital workers directly inside a cloud-based computing environment. As the cursor moves autonomously, a LAM manages your local file system, runs shell scripts in the terminal, and navigates web forms without human supervision. This chart compares performance on the Gaia benchmark, which evaluates multi-step, real-world tasks. Manus clears 86.5% of Level 1 tasks and maintains a nearly 60% success rate on Level 3 complexity, drastically outperforming traditional research models. Perplexity Computer takes this architecture further by running 19 frontier models in parallel. It uses the internet as its storage disk, acting as the read-write head for global data. Instead of relying on a single neural network, a model-agnostic kernel receives the user's high-level intent, maps it into a discrete task graph, and assigns subtasks to the most capable specialized agent. These systems bypass traditional applications entirely. The operating system is being replaced by an agentic orchestrator. Autonomous agents face an immediate architectural crisis: the exponential complexity of communicating with thousands of distinct REST APIs, live endpoints, and SQL databases. Computer science solved an identical hardware interface crisis half a century ago. Engineers at Bell Labs struggled to write software for dozens of specific, incompatible devices. Ken Thompson and Dennis Ritchie bypassed complexity with a strict design philosophy. Everything is a file. They collapsed disparate hardware resources into uniform POSIX operations. A hard drive and a network connection both responded to the exact same commands: open, read, write, and close. The Agentic file system applies this historical Unix principle to generative AI. AFS treats all heterogeneous context artifacts, text documents, vectorized memory databases, external tools, and human inputs as uniform nodes inside a strictly governed namespace. This diagram shows the dynamic mounting mechanism. A live procedural tool, like a GitHub Model Context Protocol endpoint, is mounted directly into the environment as a standard directory subtree. This eliminates the need for developers to program hundreds of custom, brittle API integrations for every new agent. Agents now only require code generation skills and a shell interface. They read an API's markdown specifications from the file system, write the necessary code, and execute it natively. By forcing every interaction through a file-based abstraction, architects ensure autonomous agents will not collapse under the weight of API fragmentation. This equation defines the agentic file system's formal architecture. External resources integrate via dynamic mount points. Metadata enforces an immutable record of provenance. Finally, the access control list maps permissions, enforcing strict isolation parameters in multi-agent networks. This mathematical structure feeds the context constructor pipeline, an automated routine that queries the AFS to gather the specific artifacts needed to formulate a prompt. The constructor ranks candidate files using a composite algorithm that weighs data freshness, semantic similarity, and the established trust of the file's owner. This visualization represents the absolute mathematical constraint of context assembly. The total token cost of all selected files must be less than or equal to W, the model's fixed token window. Because token costs are rigid, the system relies on lightweight tokenizers to dynamically re-estimate costs, compressing file fragments until they fit the active buffer. The pipeline outputs a complete context manifest. Every piece of data fed to the model is logged, versioned, and entirely auditable. The AFS transforms context engineering from an ad hoc art into a deterministic, mathematically governed data supply chain. This circular flowchart outlines the execution cycle powering large action models. Instead of waiting for a prompt, the agent loops continuously through 4 stages. In the perceive layer, vision transformers and rapid directory reads calculate the exact current state of the machine. The reason and decide layers process that state, allowing the agent to forecast the downstream consequences of its potential actions before committing to a plan. Finally, the execute layer interacts natively with the terminal shell or UI, permanently altering the system state before the cycle begins again. This continuous, recursive execution requires massive compute power. Autonomous agents consume up to 15 times more tokens than a standard passive LLM query. This structural shift forces an economic inversion. Businesses are abandoning per-seat SaaS subscriptions, moving toward an outcome economy where they pay strictly for completed tasks and successful executions. As the traditional standalone application interface recedes, a greater share of the technical and financial moat is concentrating in the orchestration layer that actually completes the task. Granting agents autonomous control over file systems introduces severe operational danger. A misaligned instruction can cascade into widespread data exfiltration or mass deletions in milliseconds. The primary attack vector exploiting this vulnerability is cross-prompt injection, or XPIA. XPA occurs when malicious instructions are embedded invisibly inside a web page or an external AFS document. When the agent reads the file, the payload executes, overriding the agent's core intent mid-workflow. This diagram illustrates the mechanics of ASI-01, Agent Goal Hijack, listed by OWASP as the apex threat facing agentic infrastructure. An attacker weaponizes the agent's ability to follow instructions against itself. Mitigating this threat requires governance as code. Engineers must isolate execution inside strict Linux sandboxes, scope permissions down to the individual token, and wire human-in-the-loop circuit breakers into critical actions. If the initial wave of large language models demonstrated that machines can understand intent, this next wave focuses on turning that understanding into a reliable industrial-grade utility. Operating at the speed of autonomous agents requires a return to the oldest, most durable abstractions in computer science, replacing conversational flexibility with the rigid precision of the file system.